Welcome students. This is going to be chapter 10.2 and we're going to get into comparing two means, and you're going to find that the structure of this chapter is very much like the structure of the last chapter. That is, we're going to start with the sampling distribution of the difference between two means instead of two proportions, and then we're going to get into confidence intervals, and we're going to get lastly into hypothesis testing. Again, each one has their subtle little differences, like we saw in 10.1. And that usually is whether you know the true population parameters or if you're estimating the true population parameters. And like before, we're going to have a little pool party at some point later. And I don't mean the swimming trunks, I mean we're going to see how to pool standard deviations. Okay, so I want to bring up one of the warm-up questions I had a few weeks ago, and I'm going to paraphrase here on my notes. But we said, hey, let's assume that men have a height that's normally distributed with a mean of 70 inches and a standard deviation of 4 inches, and women have a height that's normally distributed with a mean of 65 and a standard deviation of 3. So I think part A, we just said, what's the probability? What's the probability that one randomly selected one female is taller than one randomly selected male? And again, I apologize, I'm paraphrasing, but for time's sake, we've done this before. So what we said here is that, hey, okay, we're going to create this new random variable, and I'll call this D for the difference. And maybe in this case, it'll be the men minus the women. Which, all right, you're right. I'm not being sensitive here. I'll do the women minus the men. Good, yeah. And then we said, okay, well, if they're independently, that is, if the man's height doesn't, if the two variables are independent, that is, if the man's height doesn't affect the woman's height and vice versa, which clearly it's not going to, then we can't add the standard deviations together, but we could use the Pythagorean theorem of statistics. And we said we could add the two variances together. So in this case, to get the standard deviation, I'll just take the square root of this, and that's going to be the square root of the standard deviation of the women plus the square root of the standard deviation of the men. That's going to be 9 plus 16. That's the square root of... What, Noche? Okay. Huh? Yeah? Okay. So when we say D here, the difference is between at least one randomly selected man and one randomly selected female. And I apologize, I forgot to find the mean difference here. The mean difference is going to be, in this case, the way I defined it, the mean woman height minus the mean man height. So that's going to be that's going to be 65 minus 70. And that's where my negative comes in. The mean difference is going to be -5. And we also remember from, that was chapter 6, that anytime I combine two randomly, independently, identically distributed variables, then in this case two normally randomly distributed variables, then it also is going to be a normal distribution. So what I get out of this here, this bell curve has a mean of -5, standard deviation of 5, which we found using the Pythagorean theorem of statistics. And since we want to find the probability that one randomly selected female is going to be greater than one randomly selected male, that pretty much the way I had it again, I said D equals W minus M. If this difference is positive, then we're going to have then I'm going to have the case where the female is greater than the male. So I could do this using z-scores, for instance. This is the probability that z is going to be greater than our value 0 minus the mean, -5, over the standard deviation of 5. That's going to be the probability that z is greater than 1. And you can use the empirical rule. It gets 16, and I don't have a table in front of me, but I'm pretty sure the right answer is not quite 16%, but 15.87%. Okay, so let's switch this up now. Suppose same distributions of the men and women's height. Suppose we randomly select, I don't know, 9 females or women. Sorry, I've been calling them women. 9 women and 16 men. What's the probability now? Those are my cats are getting weird. What's the probability that that the average or the mean female height is greater than the mean male's height from these random samples? So just looking above, we got just about a 16% chance of randomly choosing a woman that's taller than a randomly selected male, which isn't super unlikely. But I have a feeling that the average of 9 women being taller than the average of 9 men is going to be a lot less likely. So we have to be a little bit careful here because we have 2 samples now. We got 2 independent random samples. And again, if I look at, say, the average of the women bar, let's look at the average height of the women. The average sample height should be just the average population height, right? 65 inches. But again, let's recall we're sampling 9 females here. Correct? Yes, sorry. So the standard deviation now of all sample means of the females is going to be the original population divided by the square root of the sample size, the original standard deviation. And the original standard deviation we said was 3, sample size was 9, so that works out to a clean 1. Now, if I look at the standard deviation of the mean average male sample, again, that should just be the actual population mean, in this case, 70 inches. But if I look at the standard deviation of all possible sample means of 16 males, again, that's going to be the population standard deviation divided by the square root of the sample size. I'll call this N2 and I'll call that N1 up there, since I took different sample sizes of each. No problem with that, right? The original population standard deviation was 4, and now we had a sample size of 16. So the standard deviation of the spread of male heights is also 1. So if I now create a new random variable, I'm going to call the average difference, and if I call that the average woman sample mean minus the average man sample mean, again I have different sample sizes, but that's cool, no problem. Then the average difference should be the average difference of the female mean, and that weird looking thing was a mean. I can't, that one's horrible. Okay, mean of the females minus the mean of the males. And again, no surprise, that's going to be 65 minus 70, or -5. Again, that means that on average, if I do this over and over and over, that on average, the difference between the men and the women is going to be -5 inches. Negative right there, it actually means that the male sample is taller. But the standard deviation now of the mean women minus the mean men is going to be, using the Pythagorean theorem of statistics, the standard deviation of women bar squared plus the standard deviation of man bar squared. It sounds weird. Woman bar, man bar, whatever. And then using these values that we calculated here above, up here and up here, that's going to be, in this case, I'm just write it here, square root of the man squared over n1 squared plus, I'm sorry, not squared because the square root, excuse me, the square root symbol went away. Excuse me. So again, I'm looking up here that if when I square this, the top will get squared, but the bottom will get squared too, and that'll just get rid of the square root sign. Good. Good job, Kitty. And that's supposed to be a W right there, excuse me, right there. That's a W. W over the standard deviation of the men squared over the sample size of them. And we got that, in our case, the numbers we calculated was 1 and 1, so the square root of 1 plus 1 is going to be the square root of 2. All right. So what we have actually just found, pretty simple, right? We actually just found the sampling distribution of, in this case, I'll call it x1 bar minus x2 bar, and the average man height minus the average female height. And it had a mean of -5, again meaning that on average the women are going to be 5 inches less than the men, and a standard deviation of square root of 2. Luckily I'm using easy numbers because I don't have a calculator with me today, and I don't know, I'm just a math dork, so I know that the square root of 2 is 1.414. So now I'm looking for the probability that the average sample height was greater than, of the females, is greater than the average height of the man. And again, I combine two randomly normally distributed variables. It's and independent normally distributed variables. So the result is going to be another normal distribution, and I could find a z-score now over 1.414. And again, I apologize, I can't get you a number right now because I don't have my calculator with me, but it's the probability that z is greater than 5 over 1.414. And I'm going to leave that last calculation to you. That's what, about 3 z-scores, give or take. So it should be pretty small, probably about 0.001, about 0.1%. Fairly unlikely again. And again, let's look at the difference between the two examples. In problem number 1, I'm just taking one single person from each. What's the probability that one man is greater than one woman? Right about 16%. And in this case, I'm looking at the average of 9 females. What's the probability the average of 9 females is going to be greater than the average of 16 males? Well, a lot less likely. That would happen about 1 in 1,000 times, 0.001. So to formalize, what we just found is what's called the sampling distribution of x1 bar minus x2 bar. Yeah, wow. And like we said before, with sampling distributions, this is always kind of the more theoretical case. It's not unlikely, but it's kind of less likely, where we actually know the true parameters of the population. Like I know what the true mean of population 1 and the true mean of population 2 is. Like in the example, I knew on average that men were 70 inches tall with a standard deviation of 4, and females were 65 inches tall on average with a standard deviation of 3, and I knew that they were normally distributed. So this is going to be a little bit more of a less likely case, a little bit more theoretical, but it's cool. It's cool. You know, under the random conditions, so we need random. What are the normal conditions going to be for this case? Well, what's the normal conditions that we've learned so far for means? Good. Either, and this applies, let me put it this way, sorry. This is going to apply to, you have to check both populations. And in theory, you could kind of mix and match these. One population could be 1, could satisfy one of the conditions, and the other could satisfy the leftover condition. So for both populations, either the population is normal to begin with, or, like in our example, or n1 is greater than 30 or equal to 30, and or n2 is greater than 30. Again, in theory, one population could have been normal to begin with, and the other population could have had a sample size of 50, and you would have satisfied the normal condition. Don't see that come up very often, but again, each one is normal. Anything normal is normal. So the center, where's the mean going to be? Well, the center is going to be whatever the difference of the two means is. Like in our case, it was -5. And then the spread, or the standard deviation, is going to be the square root of the first population squared over n1 times the population of the standard deviation of the population squared of the other one, divided by n2. And again, we have an independent condition, that 10% condition when sampling applies to both. Again, we got to check two populations. Okay. So, what happens if we don't know the standard deviation of the population? Well, what did we have to do for confidence intervals and means before when we used one population and we didn't know the standard deviation? Yeah, we used a t-distribution. And we're going to need a t-distribution again. T-distributions arise whenever we use S sub x as an estimate of the standard deviation of the population, sigma. So again, the idea is, in this case, both standard deviations are unknown. I've never seen the case arise where one is known and the other's not, so don't think too hard about that. Well, we're going to build a confidence interval off of this now. Again, what we're going to use the t-distribution here. When we use the t-distribution, we use the t-distribution with one sample. We did like S sub x over square root of n. And we're doing the same thing here now, but the standard error we would call, and in fact, let's go ahead and define this. The standard error for this x bar 1 minus x bar 2, you could also write that like we saw, x bar, standard error of x bar 1 minus x bar 2 is going to equal, again, last time standard errors arise, I'll call this S sub 1 over n1 plus S sub 2 over n2. Standard errors arise when we use unbiased estimators to estimate the population parameter. Like in this case, standard deviation / variance is an unbiased estimator. Sample standard deviation, S sub x, is an unbiased estimator of the population standard deviation, sigma. So, long story short, we're going to need this for the confidence intervals. Let's go ahead and look at the confidence intervals. So now we're going to use a confidence interval for the difference of means, two means in particular. Okay, conditions. And now we're looking at t-distributions now, guys. We're just going to be using S sub x. Again, there are z intervals out there for means, but they only occur if we know the standard deviation of the population, which I've said is typically very rare. So rare that we won't even do it. Again, random, but in this case we got to check it twice. Both independent random samples random. I'm not even going to call them random. I'm just going to say we got to use SRSs for our methods. And again, they should be independent. One sample should not influence the other sample. Our independent condition, at least when sampling, is again 10% condition for both. I think we're used to that by now. And the normal condition, and this is where life gets tricky. There's 3 options. And just checking something. Either we could use the central limit theorem, and in this case, n1 and n2 have to be greater than 30. Again, I'm not gonna mix and match anymore. We're not gonna say one can do this, one can do that. Our problems are not going to get that intricate. Or both populations are normal to begin with, or follow a normal distribution. Or, and this is more likely the case, I'm even going to put it in a different color, small sample size, which is more typical. For small sample sizes, again, a plot of both populations now. Bar graph, histogram, some kind of analysis. A graph of both populations should not be strongly skewed. Should not be strongly skewed, nor have outliers. Okay, if so, go ahead and pause it if you need more time. If so, we're going to end it on confidence intervals. I'll do one example of a confidence intervals, and we'll do hypothesis testing next time. And I essentially started with an example of the sampling distribution. I just derived the formula instead of giving you the formula ahead of time. But if you go back and look at it, I used everything there. So the actual confidence interval is, do you know what it is, Pookie? No, sorry, my cat just jumped on my book like usual. Well, it's the difference of the two means, plus or minus t star, and I'm going to get to t star in a second, times our standard error. Our standard error is s sub 1 squared over n1 plus s sub 2 squared over n2. Now I need to talk about the degrees freedom, because what happens if we have different sample size, kiddies? Who knows? Do you know? No, they don't know. Okay, you have two choices. You could either do pretty much the smallest degree freedom from the sample size, so the minimum of n1 minus n2, or n1 minus 1 or n2 minus 1. And typically we call this the conservative method. This is what you would do if you have if you don't have a calculator nearby, if you're just doing this by hand. Don't be mad about it. It's not a big deal. It's not a big deal. Or there is a crazy formula. Yeah, there is. Why are you doubting me? There's a crazy formula I'm not going to give you, but if you ever use your calculator, it actually calculates it for you. Yes, it does. Will you stop trying to refute everything I say? So typically we're going to be using the minimum, the smaller sample size minus 1. If you use technology, that's fine. Regardless, when you do these problems, you need to indicate what degree freedom you're using. Okay, we'll wrap this up with an example. Sound like a plan? Should we do a whole state plan? Do conclude? Oh man, you want to make me write this out? Alright. Okay, fine. Okay, let me make up a problem real quick. And here it is. I got some inspiration from my weird cats. So are black cats heavier than tabby cats? We randomly sample nine black cats, and their sample mean is 12.12 pounds with a standard deviation of 2.4. Both samples, and 11 tabby cats, and their sample mean was 10.31 with a standard deviation of 1.92. In both samples, a plot of both samples showed they were approximately mound-shaped with no outliers, saving you some extra work. A lot of these problems, sometimes you might be just given the raw data. You might need your calculator, L1 and L2. You could actually use the function 2varstats to find both populations, and then you can plot. You can plot actually two box plots on one graph using statplot1 and statplot2, or just call up two histograms individually if needed. But we're assuming here we got all the stats already. Okay, so I'm gonna actually not do the whole state plan do conclude. I'm actually just going to verbally say it to just save some time, and we'll kind of concentrate a little bit more on just the calculation part, and we'll deal with the whole state plan do conclude later. Hi. Hey, who started the Cultural Revolution in China? Correct. Three Stooges. It was Larry, Curly, and... Correct. Okay, finish this jingle. Ba 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 ba. Wait, hold on. Hold on. Meow 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 meow. Good job. So state. We wish to estimate the true difference between the weight of black cats and tabby cats. And we could say we wish to estimate mu1 minus mu2, where mu1 is the true mean weight of black cats, and mu2 is the true weight of correct tabby cats. Good job. And since no confidence level was given, why not? It's Friday. We'll use 95%. If the conditions are met, of course. Well, this is we plan to use a 2-sample t interval for mu1 minus mu2 if those conditions are met. Yep, random. The problem states that both cats were chosen randomly. Independent. We can certainly assume that there's more than 9 times 10, 90 black cats, and 11 times 10, 110 tabby cats in the universe, right, boys? Good job. That was the black cat, not the tabby. Normal. The problem states that both samples were approximately mound-shaped with no outliers. That should be good to go. So let's do the do. Do it. Do the do, kitties. Nope, they don't want to. So we have x bar 1 minus x bar 2 plus or minus t star s sub 1 squared over n1 plus s sub 2 squared over n2. So our first mean was 12.12 minus 10.31 plus or minus. I'm going to the back of the book and getting T star right now. We'll get that in just a second as I'm thumbing through here. But I have 2.14 was S sub 1 squared over my sample size was 9 black cats. And then 1.92 over N2 was 11, and I got to square that. That looks funny. Meow. And I'm still finding my T star. What degrees freedom am I going to use? What? I can't hear you. You have to answer that. What degrees freedom should I use? Yeah, I'm not using technology. I'm trying to find my T-table right now. I'm actually just trying to buy some time until I find my T-table. But good. I should use 8 degrees freedom because it's the smaller sample size is 9. So I'm going to use 8 degrees freedom. And I got a critical t value, and I'm sorry, I'm writing it on the side here, 2.036. I'm sorry, the decimals are really hard to make on my iPad. Okay, I'm just going to calculate both of these. Crunch these in my calculator. Alright, and those numbers just magically appeared, but I put the numbers in my calculator. And the difference between the sample means was 1.18 pounds. And the right side, the margin of error reduced to 2.12 pounds. So if I take that away, on the low side, negative 0.31, and on the high side, 3.93 pounds. Right? Don't forget our units. So so that's my confidence interval. I did the do. Now it's time to do the conclude. So we are 95% confident that the true difference in weight between black cats and tabby cats is between negative 0.31 pounds and 3.93 pounds. So can we conclude that there's a significant difference between the weight of the two types of cat? And it's funny because as I'm doing this, my cats are eating, and black cat just kicked out orange cat, tabby cat, and he's still, Noche, let him eat in peace, you fatty. Leave him alone, Noche. Noche, get over here. Pookie, you gotta stand up for yourself, bro. So no, we cannot conclude that there's a significant difference, can we? And why? Because 0 is in that confidence interval. So to wrap up the conclude part, if I were writing this out, I'd say since 0 is in our confidence interval, we cannot conclude that there is a significant difference between the two types of cats, black cats and tabby cats, that is. Okay, I think this will get you rolling. Heads up, I did assign a few homework problems. I do suggest that you do them. I realize that you've already been listening to this over 30 minutes. So this homework assignment won't be due in class next time, but you'll have an additional day, that is till Tuesday. But you should get started on this, and hopefully that all helped and made sense, and bring your questions to class. Okay, thank you guys.